So CDAC is a like a institution under MeitY, so which is mostly focused on research and development. So we are conducting this workshop or webinar on different technologies. So as a part of Future Skills Prime program. So coming to what is Future Skills, like uh, like Future Skills is the program where we have 10 emerging technologies. Future Skills is the program where we have 10 emerging technologies in it. Among that, additive manufacturing is one. So we are conducting these webinars as a promotional activity. So in FSP, we have what you can say other programs also like a GOT program where government officers can get certified. That is GOT, Government Officers Training. The other one is Bridge Course, so which is of 90 hours program, like it is self-paced program on online platform. So I'll be showing that in detail. But as a part of Future Skills, we are conducting this webinar on classification of additive manufacturing technologies. So hope I'm audible to everyone, right? Okay, coming to what is additive manufacturing. So, so here you can see additive manufacturing is a layer by layer manufacturing process. So here what happens is you will be splitting your model into a number of layers based on the quality required, and you will be deporting that layer, that material in a layer by layer manner. So here you can see the term additive manufacturing refers to a technology that grows a three-dimensional object, one superfine layer at each time, at a time. So that means like if you consider you have a product of certain height, you can consider about you have a product of 10 centimeter height, for example I'm saying 10 centimeter. If you are discretizing or layering the model into 10 layers, so of each 1 centimeter, so you'll be printing your model in a layer by layer manner, like you'll be printing one layer at a time with 1 centimeter thickness. Similarly, you will be continuing the process until the complete object get printed. So that's how the additive manufacturing works. So here you can see each successive layer bonds to the preceding layer of melted or partially melted materials. So here we have like two in some of the technologies, like in the upcoming slides I'll be saying. In some of the technologies, the material will be melted completely. In some of the technologies, it is partially melted. So that's the reason we have here each successive layer bonds to preceding layer of melted or partially melted material. And additive manufacturing is also popularly called as 3D printing. So we'll be calling additive manufacturing as 3D printing also. Here, additive manufacturing refers to complete manufacturing process, like from the stage of pre-processing, like a CAD pre-processing, then you will be slicing, then you will be preparing the setup, then you will be doing post-processing, all those things. So here you can see additive manufacturing refers to complete manufacturing process, whereas 3D printing refers to only the printing process. Like you are giving the input to the printer and it starts printing. So that is 3D printing, and additive manufacturing refers to complete manufacturing process. So that's what additive manufacturing is like. As I say, additive manufacturing is a layer by layer manufacturing process where each layer gets printed on top of the other layer, which is melted or partially melted. So after printing one layer, the previous layer gets solidified within fraction of seconds, then the next layer gets reported on the previously printed layer, and similarly the process continues until your complete model gets built. So that is what additive manufacturing is like. So coming to evolution of additive manufacturing, so additive manufacturing was evolved in between 1984 to 86. So it was from Charles Kirk. So he was a founder of the company called 3D Systems, which is a pioneer in what you can say desktop or industrial grade polymer printing. Polymer means like either it might be thermostatic polymers or thermoplastic polymers. So he was the one who founded the 3D printing. So he founded the technology called stereolithography. So which is a uh, fat polymerization technique. So here you will be using a liquid resin of thermosetting polymer resin as a raw material, and you will be using the what you can say UV light source or high intensity light as a solidification source. So you'll be projecting that light onto the liquid resin. In that way, the resin get solidified. So coming to evolution. So it was founded in between 1984 to 86 by Charles Hughes. So he's the founder of 3D printing, and he is also the managing director of 3D Systems company. So in 1992, they built the first 3D printer. In 1999, so they started using 3D printer for medical applications. Then in 2000 they have printed the miniature of kidney using 3D printer. In 2006, so uh, as the patent, like it was patented in 1984. So if you see after 20 years the patent get expired. So from as the patent got expired, from then you can see there is a large boom in additive manufacturing. So if you consider the years in between 2006, 2008 or 2010, so from that itself the evolution of 3D printing has increased drastically. Like lot of companies started their own technologies. So in that way it started. Like in 2006 they have selective laser centering machine. So this is a SLS where they will be using powdered polymer materials for manufacturing as a raw material, and they'll be using the UV light so that it can sinter the outer particle of a uh, powder, and it will be binded together. So that's was done in like 2006. In 2006, they started using for printing the prosthetic legs, all other applications like it got evolved. In 2011, and they started printing gold. In 2016, so they started using for automobile applications, then aerospace application, all that started. So this is how the evolution of 3D printing happened from 1984 or 86 to the present generation. Even now, the research work are going on different materials. So this is how the evolution of additive manufacturing technology happened. So here you can see the difference between additive manufacturing. Here I am playing a video. Hope you are able to
What is
hear me.
additive manufacturing? Additive manufacturing, also known as 3D printing, is a process that creates a physical object from a digital design. An engineer designs the object using computer-aided design, or CAD software. The 3D design file is then sliced into thin layers and uploaded to an additive manufacturing machine. The manufacturing process begins once an extremely thin layer of metal powder is spread across the platform. A heat source, such as laser or electron, then melts the first layer of the 3D design. The platform is lowered, and another layer of metal powder is spread across the platform.
So here you can see like
The
how
layering and melting
the material
process
gets
is then
liquid and
repeated
solidified.
until the part is complete. The metallic powder is removed, and a physical object is revealed. Additive manufacturing allows you to produce parts that are lighter, stronger, and more durable than traditionally made parts. Build times are faster. Engineers can add precise features and complex geometries without increasing cost. In fact, additive manufacturing is revolutionizing the way we work.
So as you have seen in the video, you can see like we start from the scratch on a build platform where we won't have any kind of workpiece. So we'll be depositing the material in a layer by layer manner. Then we'll be solidifying that. In that way, the model gets completed. So the technology you have seen in the video is SLM technology. So where you will be having the metal powder as a raw material, and you will be using what you can say carbon laser or other lasers to solidify the deposited metal powder. So you can see that there is a very less wastage of material, or we can say no wastage of material if you are doing proper DFAM, that is design for additive manufacturing. So we can design the model in such a way that we can optimize, or we can reduce the usage of supports very less. So since that by that way you can avoid the waste of material. Compared to conventional manufacturing, like here we can reduce waste of material drastically, like we will be getting very high buy to fly ratio. So here you can see the supply to manufacturing process. So generally what happens in supply to manufacturing process, you'll be taking any workpiece and you'll be carving that using any of the conventional manufacturing techniques, and you will be getting your shape out of the product. Like here you'll be starting with a chunk of material. So as you can see, there are a lot of wastage coming in form of chips. So that wastage you can avoid when you're going for additive manufacturing technology. And also like here in case of conventional manufacturing process, you have a lot of constraints regarding the manufacturing process, or you cannot do much integrated shapes. Like if you see the part like this, so which is not at all possible, like unless you are not going for multiple conventional manufacturing processes. So that those kind of parts which are very intricate in shape, so we can 3D print them easily. So that's the major advantage when you are going for additive manufacturing process. So we cannot say that like additive manufacturing process can replace the separative manufacturing process, but it can add up when there are when there are a complex parts which you are going to manufacture.
What is
So here you can see the differences between additive manufacturing process or additive manufacturing process and CNC or conventional manufacturing process. So here you will be printing the or developing the model in a layer by layer or adding the material. Here you will be removing the material from the chunk of a block. Here material is added as the part gets built. Here material is removed at the part gets built. So you have seen both in the video, right? So here you will be getting more geometrical freedom. So here we have less geometrical freedom when you compare with the additive manufacturing process. Here you will be having no wastage of material or very less waste of material. Here you will be having very high waste of material as you have seen. So we have to remove the material to get the desired shape of the object. So here you can see the additive manufacturing is suitable for low volume productions and it is suitable for higher mass production. As the manufacturing rate of additive manufacturing is very low, it's still in the development stage. So the manufacturing rate of additive manufacturing is less when you compare with the conventional manufacturing process. But even though it is not suitable for high volume, since here we have mentioned it is suitable for low volume production, but it is suitable for mass customization. Like when you are going for mass customized models, additive manufacturing plays ahead when you compare with the conventional manufacturing process. So here you can see additive manufacturing we can adapt when there is a mass customization. You can go for conventional manufacturing when there is a mass production. So that's the advantage of additive manufacturing. Next, coming to like here we have very less tolerance when you compare with the CNC or conventional manufacturing process. Here you get high tolerance values. So this is one more drawback in case of additive manufacturing. But we can get that like tolerances after after 3D print the complex part. You can go for post processing operations and you can get the required tolerances. So by while 3D printing itself, you can maintain some block like some extra material on top of the model, and then you can go for post processing. In that way, you can achieve the tolerances. Here the speeds are less. Here the speeds are more. So as I said, like it is conventional manufacturing is suitable for mass production, and this is used for mass customization. The speeds are less when you compare with the conventional manufacturing process. So these are the differences between additive manufacturing process and conventional manufacturing processes. So here, if you see the advantages, like here, the first advantage lead time reduction. So when you are going for any kind of product development, so in the process of design iterations, so it requires a lot of time to get the part in hand when you are going for conventional manufacturing process. But when you are going to adapt additive manufacturing process, you can print your part within no time. Like if your day is ready by end of the day, you can start printing in the evening. By the next day morning, your part will be 3D printed. So in that way, you can reduce the lead time of product development. So here you can do topology optimization. So topology optimization refers to like optimizing the weight of the part. So there are other like other what you can say software like a simulation software where you can optimize the weight of the part without losing any kind of strength parameters. So you can reduce the weight of the part. So that is one advantage. So weight reduction, as I said, and part consolidation. Like if you are having n number of parts, like consider your assembly has around 8 to 10 number of parts. So when you're going for conventional manufacturing process, so you are getting more number of parts because of the constraints we have in conventional manufacturing process. But when you are going to adapt um, additive manufacturing in your design cycle, then you can consolidate those n number of like 8 to 10 number of parts into 2 to 3 parts, in which way you can reduce number of parts in an assembly. Like you don't have to deal with more supply chain issues as the number of parts increase in your assembly, so you have to deal with a lot of like more number of supply chain issues when you are consolidating those parts. Like even if it is feasible, if it is the build size is proper and if your part size within that limit, you can print that 8 to 10 parts in one go. Like you can consolidate that part into a single part. So that's the advantage. One more advantage we get when you are going for additive manufacturing. So here we have one more advantage: mass customization. So you can print mass customized models in a single build. Like if you are going for hearing aids, so each patient will have their own ear structure. So you can print those kind of models in a single build. So that is what mass customization is like. If you're going for medical aligners, so as an individual patient has their own jawline, so you can do those kind of mass customizations when you're going for additive manufacturing. Next, we have high buy to fly ratio. So this also plays a major role when you are going for aerospace applications, where the weight of the part matters a lot, as it saves a lot of fuel for them. So as we have high buy to fly ratio, this also plays an advantage. Yeah, like here we don't have very less waste. Here we have very less waste of material or no waste of material, what we can say. So even if you are having a support structures, so that might be because like if you are going for any metal 3D printing, so there we'll be using support structures as a heat dissipating agents. So if you are printing a part which has higher build area contact with the build plate or the platform which you are printing, so due to excessive heat coming from the build plate because of the high intensity laser, like it will be more than 1000 or 1400 degrees centigrade. So to dissipate that heat from the part, so we have to provide support structures which will be dissipating the heat. So that is one more advantage we have, like high butterfly ratio. Next, here we have high geometrical freedom and less constraints when you compare with the conventional manufacturing process. Next, we can do the distributed manufacturing process. Like if there is any part which is going to extinguish, like consider some automobile part, like automobile or car, so which was manufactured in 1990s or 2000s. So storing of those kind of spare parts for those kind of cars will be difficult. Like we have to do a lot of inventory management. So when you're going to adapt the additive manufacturing process, like you can digitalize those model, you can save the CAD file. So whenever there is a requirement of the spare part, you can 3D print it directly wherever you want. So that is distributed manufacturing and production. You can do manufacturing and production wherever you want. So here we have very less waste of material, and we can do low volume and mid volume production when you're going for additive manufacturing process, as it is not suitable for high volume production. So here, one more advantage, like on demand and on location production. So you can manufacture your part whenever there is on, like you just need a small printer through 3D print that part if you are going for any polymer 3D printing. So these are the various advantages we have when you are going for additive manufacturing. So here coming to AM process here. So what is the sequence of steps we follow to 3D print a part? So these are the various steps, like we have around 7 to 8 steps. First is CAD model or 3D model. So you require a 3D model to 3D print your part. So either you can get that from any of the CAD modeling softwares which you are familiar with, like you can use SolidWorks, you can use Fusion 360, you can use Siemens NX or whatever the solid modeling software you have. You can use that and you can create your part. Or if you have any old part which you want to digitalize, you can go for reverse engineering like 3D scanning and you can digitalize those part. So first we require is CAD model or 3D model. So then after we have to convert that into a STL file format, that is a standard tessellation language. So where it will be converting your model into the mesh like structure in a triangular formats. So this is a what you can say uh, vastly used file format for 3D printing manufacturing process. So you have to convert the file into HTML file format, then you have to do slicing. So as I said, slicing is a discretization of your part based on the layers you require. So in slicing software, we will be importing the HTML file which we converted from CAD modeling, and we'll be converting that into layers. Here you can see your this model is converted into the number of layers. So based on the quality we require. So from this slicing software, we'll develop the tool path which is understandable by the 3D printer. So then you have to do machine setup, where you will be setting up your machine, you will be loading the raw material, you will be calibrating the printer. Calibrating the printer means, yeah, you will be adjusting the distance of build plate from the uh, extrusion head. So all these things you will be doing in machine setup. Then you will be 3D printing the model, then you will be removing the model from the build plate and you'll be doing the post processing. So even in removal, you have like a different process for different technologies. In post processing, you will be following different sequence of operations. How do you post process 3D printed part? Like you will be doing curing after 3D printing, then you will be doing other kind of what surface roughness post processing techniques on the 3D printed part. Next application. So this is the sequence of process which we follow in additive manufacturing process. So coming to applications. So additive manufacturing can be used for prototyping, like in the prototyping process, you can use for tooling, like when you're going for a conformal cooling inside the tool head, you can go for tooling and you can use for performance improvement, and you can go for production, like low volume production. You can go for mass customization, you can go for personalization, you can do for use for spare part maintenance, repair. Even you can do repair on the 3D printed part, like if any of the large part got damaged, so you can do DD process, like what is DD process, I will be showing in next slide, next couple of slides. But you can do repair, like if there is any broken area in it part, you can deploy the material there, and in that way you can repair the old part also. Then you can use it in art, you can use it in design, architect. So there is no specific industry where we cannot use 3D printing, like other than cloth manufacturing or something, but mostly in a physical objects you can use 3D printing in all the applications. So these are the applications of additive manufacturing. So next, coming to classification of additive manufacturing process based on ASTM standards, so which is our major topic. So as per ASTM standard, there are seven different types of additive manufacturing technologies. So among that, so we have material extrusion, one, sheet metal lamination, the other one blended jetting, VAT polymerization. So VAT polymerization is the first technology which was invented by Charles Hugh in 1984, as I said. Like he invented stereolithography, so which is based on the liquid resin. Uh, VAT means like resin tank, what we call. So next we have powder bed fusion. Next we have material jetting. So next we have direct energy deposition. So there are seven different types of technology. So the building process remains the same in most of the technologies. The major difference between all these seven technologies is the raw material which we are going to use. So if you see here in metal extrusion, so we'll be using the raw material in a wire form. So if you are going for VAT polymerization, we are going to use raw material in a resin form, like in a liquid form. Like if you are going for powder bed fusion, here we'll be using raw material in a powder form, like metal powder. And like based on the raw material, we have to choose a suitable solidification source to develop a 3D model, right? So in case of material extrusion, we'll be having a material in a wire form. So we'll be melting the wire and we'll be depositing in a layer by layer process. When you're going for wet polymerization technology, so here you will be having a raw material in resin form. So to cure that resin, we require a solidification source. So either it might be a high intensity laser or UV light. So as thermosetting polymers are light sensitive, so when you're projecting the light on that liquid area wherever you want to build the part, so it gets solidified. So in that way you'll be developing. So if you go to powder bed fusion, since we are using metal powder, so it is selective layer melting, electron beam melting, which is in powder bed fusion. So here we'll be using what you can say laser, like a carbon fiber laser or some other lasers to solidify. In electron beam melting, you will be using electron beam to melt the powder and we'll be solidifying that. So in that way, in every technology, like the build process remains the same. Like you'll be having a material, it get deployed on a build. If you consider this is a build platform, your material get deployed on build platform, it gets solidified, and your build plate will be lowering, and top of that, next layer will be deployed. So the process continues similar in all the technologies. Just the raw material which we are going to use and solidification source, which is going to solidify the part, is changes is will be changing. So that is a major difference between all the seven technologies. So we are going to see all the seven technologies detailedly in the present webinar. So here you can see these are the seven different technologies. One is VAT polymerization, which is having liquid resin as a raw material. Material extrusion, we have wire form as a raw material. Material jetting, here you will be using the powder material, and you will be jetting the material wherever it is required. Here you will be having binder jetting. Binder jetting means like you will be spreading the layer first, then you will be jetting the binder wherever it is required so that it can solidify. Next we have powder bed fusion. So where you will be having powder metal powder as a raw material. Solidification source might be like what you can say, high intensity like laser, or you will be using electron beam. Next we have one more DED, direct energy deposition, which is used in uh, repair, like in applications I have shown, right? Like we can use 3D printing for repairing the parts also. So we'll be using DED process in that case. Next we have sheet metal lamination. So we cannot call this completely an additive manufacturing process, but I'll be explaining during the technology. Like it is a combination of additive manufacturing as well as separative manufacturing. You can see. So these are the different technologies we have. So coming to here, these are the pioneers in their domains. Like in VAT polymerization, we have 3D systems as a pioneer, like Envision Tech. All these are pioneers. Like if you are going for material extrusion, we have Statistics, Ultimaker, Megaboard. These are the pioneers. If you are going for material jetting, we have Statistics and 3D systems. All this, and binder jetting, we have voxel jet, so X1. So these are the printers which we can use sand also as a raw material. So these are the pioneers in their what you can say technology. Next, powder bed fusion, we have HP, we have EOS 3D systems, we have SLM, Reniksha. So these are the pioneers brands in the technologies. So similarly, we have DED and sheet metal lamination. So starting with the material extrusion. So what happens in case of material extrusion is, like as I said, so we'll be having a raw material in a wire form. So in your material extrusion process, what happens? So you'll be having a raw material, so which we call filament here. So we'll be having a roller here, so which will be pulling the filament inside towards the nozzle. So nozzle is the area where you will be having a thermocouple which will be heating the filament. So based on the filament, like there are different types of filaments, like based on the filament it will heat the filament in the nozzle, and it will be depositing the filament wherever it is required. So this is what happens in case of FDM. So FDM is future deposit modeling, or like in some brands, like if you see Ultimaker, they call it as FFF, which is fused filament fabrication. So if you see here, like your filament is getting inserted, it will be pulled inside, and your filament will be melted and it will be deposited. So this is a process which happens inside the printer. But if you see from the outside, so this is your build platform on which your complete model get built. So these are the extrusion heads. So this is the extrusion head, means like this complete setup will be inside the extrusion head, and these are the nozzles we have. So from where the material get deposited. So this is the build. Now this is the actual model, and this is a support model. So since we have two different materials, so one we can use two different extrusion heads. So we can use one for model material, the other one for support material. So what happens here, like you will be loading your model, so it will be deposited here. After completing of one layer, your build plate will be lowering by whatever the layer resolution you have defined in the slicing software. So then the next layer get printed. So this is a process which happens in FDM, or metal extrusion. So here you can see a video, small video, what happens in a additive manufacturing process.
Fused deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
So as you have seen in the video, so that's how I do like a FDM process work. Like you will be having two different extrusion heads, one for model material and the other one for support material. So the white color part which you have seen is the support material. The black color one is the actual model material. So next, so these are the three different what you can constructions we have when you are going for FDM process. So the one is Cartesian type 3D printer, one is polar type 3D printer, the other one is delta type 3D printer. So what happens in case of Cartesian type 3D printer is your build plate will be moving in Z direction. So and the movement or the printing direction will be given to the extruder in XY direction. So once by the starting of every layer, so your build plate will be raising up until it reaches the extrusion head. Then after reaching that extrusion head, your extrusion head will be moving the direction and it will be deployed in the material wherever it is required. So that is what happens in the Cartesian type. But in case of polar type, here your this z-axis has both the motions. One is like a Z motion where you will be adjusting the height. The other one is Y motion where you will be where it will compensate in the Y direction also. And X orientation is compensated by the rotating disc. So in that way, your model will be 3D printed completely, like until the complete model get printed. Like how you can say in the starting of the layer, your extrusion head will come down, and your rotating disc will be here, and it will have Y coordinates also. So it will rotate, this disc will rotate in a clockwise and anti-clockwise manner, and this Y direction will be controlled by what you can say Z axis itself, and in that way complete model will be getting 3D printed. In case of delta, so here your extrusion head can reach to all the parts like by adjusting the sliding here. So when you're doing the slicing, so it will give the coordinates like how much the sliding should happen, like how much what length the sliding should happen on the all the axes. In that way, it will coordinate the extrusion head. So these are the three different types of 3D printers we have in case of FDM technology. So here we have, if you see, there are different types of materials also. Like unlike conventional manufacturing process, we have different materials in case of IT manufacturing. Like we have high performance material, we have engineering grade material, we have commodity material. So in that, some of them are semi-crystalline, some of them are amorphous, which don't have any defined shape. Like in that we have ABS, mostly used for industry, like medical application. We have PVC, we have HIPS. These are all the mostly used for medical application. We have PC polycarbonate, which is high temperature resistant material. We have PA polyamide, which is used for engineering grade. We have TPU, which is a flexible material. We have PETG, we have PEEK, which has very high performance. So these are materials we have in case of additive manufacturing uh, in FDM based technology. So next coming to VAT polymerization, so which is a very first technology in case of 3D printing, you can see. So here we'll be using a liquid resin. As I said, the raw material and the solidification source only changes. The other setup of the 3D printer will be same. Like here you can see, so here you have a high intensity light source at the bottom of the 3D printer. or in some setup it will be on the top also. So in this also we have two different processes. I'll be explaining that in next. So you'll be having a liquid resin. The orange color one is a liquid resin we have here. So after completing every layer, your build plate will be raising up, and the next layer gets already built on the previously printed layer. So this is a printer setup we have. So here this is called elevator. Next we have 3D printed part. So this is the build platform. So here we have sweeper, so which will be leveling the liquid. So here we have liquid polymer, which is in orange color, and you will be having XY scanning mirrors, so which will be deflecting the light source or solidification source wherever we want to solidify the part, and we will be having a laser chamber here. So this is the setup of wet polymerization technology. So here you can see the video how it happens.
The Form 1 Plus is a stereolithography 3D printer. Today, we're going to take a look at how it works and put it to the test against parts from an extrusion-based machine. Let's start by taking a closer look at the printer. When we open up the light-blocking cover, we can see a build platform inside. This metal plate is where the parts are made. Underneath the build platform is a resin tank. This clear window gives the ultraviolet laser a path to cure the resin. To start a print, we'll upload a file and fill up the resin tank to the indicator line.
Sorry.
You can see the laser passing back and forth inside, hardening the liquid plastic. We'll take our printout and wash it in rubbing alcohol to get the excess resin off. The flower comes with supports on it, and we'll snip them off to finish the piece. Stereolithography is known for producing extreme detail with layers down to 4 times finer than a human hair. The Form 1 Plus lets us take advantage of a library of materials, so we made some other parts to show what these resins can do. A castable resin gives jewelers and engineers an inexpensive way to produce metal parts. This flexible resin is great for simulating different textures, and as we can see, this tough resin can really take a hit. Now let's compare how the Form 1 Plus parts stand up against a filament printer. The stereolithography part
So
comes
here they
out
are
nice and
comparing the
smooth,
FDM
but we
3D
can
printers
see
with
and
the
feel
SLA
the
3D
ridges
printers.
on the cup printed with filament. When we break this sample piece, you can see that filament parts quickly snap along the layer lines. The SLA process creates a chemical bond, so our prints take much more force.
So this is a bottom-up type of
Today,
3D
we took
printer.
a look at how stereolithography printers work, the types of resins they can print with, and what makes the parts stand out against other desktop machines. If you liked our intro to stereolithography 3D printing, check out some of our other videos. If there are more subjects you'd like to see us cover, please let us know in the comments, and we'll see you next time.
So as you have seen, so this is how the SLA type of flat polymerization works. Like your layer of liquid resin will be deposited and it will be solidified using the high intensity light, and the next layer get deposited again. Your blade will be lowering down, or it will be going up based on the printer setup we have. Like in some of the 3D printers, this is top down, where your build plate will be moving from top to bottom, where your laser setup will be on the top, and in some printers it will be from bottom up. So here if you see this one, so this is the bottom of 3D printer. So your build plate will be moving in the upward direction after completing every layer, and you have complete laser setup at the bottom. So now I'll be showing the both the 3D printers, like what it is. So here you can see, so one is top down 3D printer, one is bottom of 3D printer. So in top down 3D printer, you will be having a laser setup at the top of the 3D printer. So in which way, after completing of each layer, like if you consider, so this is your build platform and this is your model. So after completing the model, like one layer, your build plate will go down. So after going down, your recoater will spread the next layer of liquid resin, and your solidification source will solidify wherever it is required. So in that way it continues until the product gets built. So that is what happens in case of top down. When coming to bottom up, so it is a mostly same setup, but here this will be your build platform. So this will be your model after completing a particular layer. So your what you can say, build plate will be lifting up in the resin tank itself. So it will have resin. This is throughout resin we have. So it will be lifting up in the resin tank itself. So in that way the next layer will be solidified by the light source, which is present at the bottom of the 3D printer setup. So here, if you see in this process, like bottom of process, your complete model is submerged inside the resin tank. So that is the main difference between the top down and bottom up. So here we can see the differences, major differences between bottom up and top down. So bottom up type of 3D printers are low cost and they are widely available, and top down are technology has very large build size. Like build size, build size means the platform on which the 3D model is getting developed. So when you compare bottom up with the top down, your bottom up printers will be having less build area compared to top down. So the reason for it also I'll be telling, like top down has very high build area and it has faster build times. So disadvantages coming to bottom up. So it has smaller build area. You cannot build large models. Next you have smaller material range. So there, as there is like these are cheap printers, so we don't have wide material range. Next, it requires more processing time due to extensive use of support. So in this bottom up type, what happens? Since your model is lifting from bottom to top, like if you see, so this is your build platform, so on which your model is built. So you are moving against the gravitational force. So to hold the model to the build plate, we need more supports to hold the model to the build plate. So for that way, it requires more support and it requires more support time to remove the supports also. So that is a major drawback of bottom up type, and you don't have higher build area. So that is one more reason, because if you have higher build area, you will be printing the larger models. To stick the larger models in bottom up type, so it has to use extensive support to hold those models to the build platform. So which require a lot of support, and in return it will increase the post processing time. So that is a major drawback. So that's the reason we don't have higher build areas when you are going for bottom up type of 3D printer. So in top down, we have like a disadvantage like higher cost, since this has larger build area. The cost of the printers will be high, and we require a specialist operator for operating these materials, because we have to store the material properly, and we have to uh, what you can say, preheat the materials properly before the 3D printing. So all those challenges we have. So we require a specialist operator. Next, coming to dimensional accuracy, the accuracy of the parts is like 0.5%. Here we have more dimensional accuracy. So that is a one more reason why the top-down 3D printers are costly. So these are the major differences between the bottom-up and top-down type of SLA 3D printers, which is VAT polymerization. So here we have different material ranges. So here you can see the strength parameters like iodide impact test or elongation tensile. So these are the various strengths we have. Like we have different resins like standard and clear. Which we have tough resin, we have durable resin, we have heat resistant resin, we have ceramic resin. Now lot of materials have came, like we have dental resin, we have castable resin also. So based on the requirement, you can use your materials. So these are the different materials we have. In that also you will be coming in with, but one drawback here is like you won't get this kind of resins in different colors. Like the color options are very less. So when you are going to use this technology for aesthetic purpose, so the color options are less. So you have to choose among whatever the colors we have. So these are the material properties we have. Next, DLP. So DLP is similar to SLA technology which we have seen previously, but the only difference is there your like after completing of every layer, so your scanner will be moving to area wherever it has to sulfur. Like if you see this product at this layer, so your scanner has to move all these areas to scan. But in case of DLP, your complete layer will be solidified in one go. So you will be having a picture, so which is of a voxel. So where in every layer, so it will be projecting the light from those picture wherever it is required. So in that way, the printing process of DLP is high. Like here you can see, here you have lens, so it will be projecting the light in one go. So in that way your complete layer gets solidified in one time. But in case of SLA, your laser has to move to individual point to solidify that. So that is the major difference between the SLA and DLP process. The other construction will be same, like it too has top down and bottom up. So this is a bottom up type, and the other one will be having top down. So rest of the like raw material will be same, and solvent source will be same, but here you will be solidifying the complete layer in a single go. So, which you'll be getting the faster build, but the quality will be less when you compare with the SLA technology. So you can see the video here. So this is bottom up type of printer. So this is a liquid resin which they are pouring. So build area, like build platform will be dipped inside the resin tank, and it will be lifting up. So here you can see in the video we have lot of supports holding the part, since we are lifting it against the gravitational force. So we have to do lot of force thrusting also here. So that's how the process happens in DLP. So the construction of the 3D printer will be similar to SLA process itself. Only the not even the solidification source, only the what you can say, projection of solidification source will be different. The rest of the things will be same. So this is a comparison between the DLP and SLA. So SLA, if you see here in the critical areas, the integrated features also come in detail. But if you see in DLP, it is not that clear or not that great when you compare with the SLA process. As in SLA, you can see your what you can say, solidification source is moving to each and every position individually until it gets solidified. But here, if you see in case of DLP, your complete light is projected in a single go. So as the build rate is faster, as well as the solidification source won't reach every point individually. So the quality of print varies when you compare with the SLA. So here you can use SLA when you are going for much detailed parts, and SLA like DLP you can use for the where you require the faster build area with uh, a decent finish, or where there are no integrated features. So this is the major difference between the SLA and DLP. So next we have sheet metal lamination. So this is like a combination of additive manufacturing and conventional manufacturing. Here you can see. So here like you'll be one layer of sheet metal will be uh, uh, kept on top of the previous sheet metal, and it will be welded through sanitode, and it will be uh, using conventional technique to get the shape of the part. But the advantages of sheet metal lamination is here also you can do intricate shapes, which is not possible through general conventional manufacturing process. You can see in the video.
Ultrasonic consolidation produces direct metal parts from CAD data by ultrasonically welding layers of coiled aluminum foil strips to a prepared metal substrate. As the foil strips are placed on the substrate, a tool called the sonotrode uses high-frequency vibratory energy and moderate force to disrupt the interface surfaces, inducing interatomic attraction and metallurgical bonding between the foil and the substrate surfaces. Once ultrasonically welded, the layer is then milled to the cross-sectional shape
Here you
defined by
can
the
see we are
CAD
removing
data.
the material through general conventional
This
manufacturing process.
process
The
of
wastage
adding
is more, but
material
you
to
can
a
get
previous
the
layer
detail or
and
complex
then
parts when you are going
removing
for
the
sheet metal
excess
lamination or ultrasonic
continues until the
lamination.
part is complete. Like other rapid prototyping processes, ultrasonic consolidation also allows for the buildup of complex geometries, overhangs, and enclosures within a part. Ultrasonic consolidation can be used to bond a variety of similar and dissimilar metals, as well as certain ceramic metal combinations.
So as you have seen, so it is a combination of conventional and additive manufacturing process. So here your sanitode will deposit the metal sheet, then it will be milled wherever we require. So but if you compare conventional manufacturing and additive manufacturing, here you can get the complex geometries, but waste of material remains the same. So that is about the sheet metal lamination. So next we have in sheet metal laminated object manufacturing. It is also similar, but here you will be using tungsten wire to cut the part wherever it is required. You can see in the video. This is the construction of laminated object manufacturing machine.
Shutterstock music. Shutterstock music.
So here you are will be cutting the material wherever it is required. That way your complete model is built. And after completing one layer, next layer of sheet metal paper
Shutterstock music.
shift to the previous printed object. So the process continues until your complete
Shutterstock
model get
music.
developed. But here the wastage of material will be the same, like in case of sheet metal lamination, the wastage will be more, but you can achieve the critical geometries also when you're going for sheet metal lamination.
Shutterstock music. Shutterstock music.
So in this process, your laminated object manufacturing process will be working like it is similar to the sheet metal lamination. So next coming to powder bed fusion. So this is one of the widely used technology when you are going for metal additive manufacturing process. So in that we have two, like one is selective laser melting SLM process. We have one more called EBM, electron beam melting. So the construction of the 3D printer remains the same as you can see. So this is the construction of 3D printer. So here you will be having a build platform, so which will be raising up and lowering down. So after completing of every layer. So here we have dispenser duct. So where it will be having the raw material. So after completing every layer, so this is called recoater. So this will be spreading the material on the build platform after completing every layer, and excess material will be dumped here. So after spreading all throughout, so whatever the excess material is there, it goes into the collector tank. So then your next layer will be solidified, and after completing of one layer, the next layer of powder metal will be deposited by recoater. So here you have the solidification source. So here we are using what you can say laser as a solidification source. Either it might be carbon laser or other lasers will be. And here you have scanner, so which will be deflecting the laser direction wherever you have to solidify the part. And here we have to maintain inert gas inside the chamber. Either it might be argon or other inert gases. So inside the chamber. So this is the construction of uh, SLM process. Here you can see we have CO2 laser. So this is the recoater we have. So it will be spreading the material, and this is the collector tank. So where it will be collecting the excess material after completing one layer. So this is your build platform which will be getting down such that the next layer of water can be deposited. So the process continues until the complete metal part got 3D printed. So you can see in the video. So this is the slicing software we have. So we are importing the HTML file. So after importing the HTML file, so we have to set all these parameters, what kind of supports you want, all these things. So here we have support definition, we have optimization, all these things. You'll be learning that detailedly like when you are undergoing any kind of GOT training or bridge course. So you can multiply the parts also inside the slicing software. So and you can arrange the parts on the build platform. You can arrange the support structure, what kind of support structures you want. So this is the construction of 3D printer. So here you can see after completing one layer, your laser is curing the part. So as we have multiple parts, so the laser moves to every point and it will solidify. So after completing one layer, so this is the recoater we have here, so where we have excess powder. So it will be spreading material on this platform. So here we have to maintain the inert gas inside the chamber. It might be organ or other inert gases. So after completing one layer, so your recoater is spreading the powder here. You can see. The collection tank we have. So this is a dual type, but in recent 3D printers we have collection tank in the other side itself, so that it can optimize the travel time in the other direction. So here it is spreading the powder, and you can see in the video how the part is going. So here you are using fiber laser which is of 400 watts to 1 kilowatt. Based on the raw material you are using, powder you are going to use. After completing, we have to remove the powder using those slots we have, and we have to take out the part. So you can reuse the part, reuse the powder also. So you have to be careful when you are removing the part, because those border particles will be very nano, like it will be very less microns, so it might enter into your nose also, like you can inhale that. So you have to take precautions, like you can use 3M mask or other things. So those are the support structures we have. So later on you can do post processing on these 3D printed parts. So you can remove the part from the build plate, and this is the build platform, and you can do laser cutting and other operations to remove the parts from the build plate. So these are the parts we have. So in that way, SLM process works. Next coming, so here you can see, like we are using the solidification source we are using is laser beam, like either it might be CO2 laser. Next we have materials. So we have vast number of materials, but these are the mostly like aluminum, titanium, let's see, copper, chromium, or inconel or other materials we'll be using. Next, feeding mechanism. Here we have recorder as a feeding mechanism, as you have seen in the video. Like atmosphere, we have to use inert gas, either it might be argon or nitrogen. Next, layer thickness we can print from 200 like 20 microns to 100 microns. That is 0.02 mm to 0.1 mm. So that's the precision which you will be getting when you're going for metal 3D printing. Next, the laser spot size is like 50 microns to 500 microns. The maximum build area we have in present 3D printers is 500 by 500 by 500. Like if you want to print larger build platform, then you can go for a DD process, or you can split your model into two parts, and then you can 3D print, and then you can go for conventional welding process. So this is the specifications of SLM machine we have. So next, coming to EBM process. As I said, like SLM and EBM has both, like both the 3D printers has similar setup like we have in SLA and DLP. Only the solidification source. There we have high intensity laser. Here we are using electron beam as a solidification source, and there we have to maintain the uh, inert gases. Either it might be argon or nitrogen to inside the chamber. Here we are going to use a vacuum as a, what you can say, chamber gas which we are going to use. The other construction will be similar, like here you have dispenser, and like here you have a recorder where it will be spreading the material, and you will be having the dispenser similarly. So this is a construction of EBM, that is electron beam melting. So you can see in the video it is mostly similar, like you can hardly notice the difference. The only certification
Additive
difference.
manufacturing offers greater freedom in design and allows for the creation of optimized parts that are not constrained by the limits of traditional manufacturing. RCAM EBM has the unique ability to tightly stack parts within the build in order to increase productivity. An optimized build file is sliced and loaded into the RCAM EBM system. Following this, metal powder is loaded into the machine.
So here you can see the
The
construction
build
is similar
chamber
to
is then
the
closed and a vacuum is
SLM
created
process.
to ensure a clean, controlled environment that allows for the processing of reactive material. Next, RCAM EBM's powder layering system evenly
So recorder is
distributes a
splitting the
thin
powder,
layer of powder on the build area. A powerful
and the
6
electron
kilowatt
beam is
electron
solidifying
beam
the
heats
part
the
wherever
powder
it is
bed to the
required.
optimal ambient temperature and then proceeds to melt the powder. First, contour melting and then hatch
So
melting.
countering the perimeter of the part, and
The
hatch is the
electron
internal
beam
area.
unit generating the beam contains no moving parts, allowing for extremely fast and accurate beam control. The build environment is kept hot, reaching temperatures exceeding 1000 degrees Celsius, resulting in no residual stresses
So as
and
the temperature
allowing
is
for
more
the
inside
processing
the
of crack-prone materials.
chamber, so we have to
As
provide
each layer is
support
completed,
support
the
such that it
build
won't
is lowered and a
warp
fresh
the
layer of
3D
build
printed part.
powder is raked over it. This process repeats, growing the build one layer at a time. When the build is complete, the tank is extracted and the RCAM EBM machine is prepared for the next build.
So that's how EBM process work, which is similar to SLM process. So coming to the specifications of the machine. So here we are using electron beam as a solidification source. In case of SLM, we use the laser as a solidification source. And materials, similar materials like SLM process, like feeding mechanism, recorder. So atmosphere, there we have used the inert gas. Here we are going to use vacuum. Layer thickness, we have 50 microns to 200 microns. But in case of SLM, we have 20 microns to 100 microns. Here the layer thickness is more, like we cannot print much finer parts compared to the SLM process. Next, laser spot size, which is from 140 microns to 250 microns, and the build area is 250 by 430 into 430 we will be having. So these are the machine properties of EBM manufacturing process. So these are the different materials we have, which is similar to which are both for SLM and EBM. So we have different what we can compositions in aluminum. We have different composition in titanium. We have inconel 700, which is mostly used. We have copper chromium. So these are the materials we have. Based on the requirement, we can choose our material. And if you want the other metal, you can you like you can use the technology in material development also, like with using different combinations of materials. So here we have DD data deviation. So this is similar to SLM process, but the major difference is there you have a restricted build area, but here in case of DD process, so you won't be having any build area. Here it is like a robotic manipulator which we have. So it will be moving in all the directions. Here you will be having rotary table. So and you will be having a what you can say laser beam at the center, and powder will be depositing from the sides. So in that way you can deposit the material wherever it is required, and you can print large number of parts, but the quality of part won't be great when you compare with the SLM and EBM process. Later on that you can do the post processing. So this DD process will be mostly used for repairing of a part or when you're going to print larger parts. So this is a construction of the printer. So here we have laser setup. So where we will be putting the laser from the manipulator. So this is a gas chamber. So from where you will be getting the inert gases. And this is a build platform. You will be having a rotary table. And this is motion control unit. So this is a construction of DD machine in case of lens. And we have one more with regard to like which is similar to EBM also. We can see that also. So here you can see the solid source is high intensity laser beam, which is similar to SLM, and powder jet. Like there we have feedstock mechanism as a recoder. Here we'll be using the powder directly as we have robotic manipulator. So it will be going wherever it is required, and it will be spreading the material, and it will be curing that also. So atmosphere we have powder jet shredded with inert gas. So as we require inert gas in SLM process, so our raw material or the solidification source will be shredded with the inert gas around it. Next, we have materials. We have different materials. Like compared to SLM, there are less materials, but we have sufficient number of materials even in case of DD process also. With like metal, ceramic, multiple material, you can do different combinations. Next, maximum build area we have 1200 by 800 by 800, but in case of SLM we have 500 by 500 by 500. So that is a major use of DD process. Like here you get higher build areas, like you can use for repairing of the parts, and you can print larger parts. So that is the reason why we have the DD technology. So and the deposition size is 800 microns to 2400 microns. So this is the machine parameters of lens machine, that's laser energy net shaping. So this is a video you can see. The construction we're going to direct video. These are the materials we have. So we have to pour the material in the recorders, or here we have powder jet, so we have to pour the material. So this is the process how it works. So here you will be having a powder jet of raw material. So and you will be having a what you can high intensity laser shredded with the inert gas, and it will be solidifying the part. So surface toughness ranges from 12 to 25 RF. We can see. So here we have quad laser with our 4 lasers. So it will be depositing the metal wherever it is required, and it will be solidifying that. So and the process continues until your complete model get built. So this will be like we can use this for laser cladding also. So where you are going to repair the parts. So that is regarding lens. Oh, this is EBM, so which is similar to like which is one more technology under DD, which is similar to lens, but here you will be having the raw material in a wire form. So and similarly, like electron beam will be solidifying the deposited wire form, and it will be in a what you can say vacuum chamber. So this is a construction. So this is a manipulator we have, and this is a build platform which will be rotating. And this is an object which is like similar, like it is similar to EBM. Like it is a combination of EBM and lens. We can say the feedstock mechanism will be changing. So this is a construction of EBM, that is electron beam additive manufacturing, which comes under DD, direct energy deposition. So these are the properties. One is like a solid source is electron beam gun. So feedstock mechanism is wide deposition, which is similar to FDM, and atmosphere, like we have to maintain the vacuum temperature. These are the different materials we have: titanium, steel, nickel, superalloys. We can use like can develop the material in a wire form and we can use. Here you can see the build area, which is 7,000, like approximately 7,200 and 1,200. So which is very high when you compare with the length, like laser energy net shaping, which we have seen previously. So that's the reason, like in DD also EBAM is the widely used technology. In case of DD, that is direct energy deposition, like Saki side to manufacturing as a pioneer in this technology. They will be printing large like turbine blades and all those things uh, using EBAM technology. So here the build size is like a laser spot size is 800 microns to 2,400 microns. So this is a construction of like a machine properties of EBAM. So you can see the video, but the surface roughness is very bad
Time
when you
and
compare
cost
with
it used to
the
take. With
other
Siaki's exclusive
process.
electron beam additive manufacturing, or EBAM for short, metal 3D printing is not limited by part size, material, or geometry. You can manufacture parts and structures that exceed 19 feet in length, 4 feet wide, 4 feet high, and 8 feet in diameter, made
So
from
it has very
virtually
huge
any
build
metal,
area. So this is the
including
build area
Inconel and
which we have.
stainless steels, and refractory alloys like titanium and tantalum. How does the EBAM process work? Starting with a 3D
So
model
it has a
from a
rotary
CAD
table.
program,
So
Siaki's
you can
fully
see here.
articulated moving electron beam gun deposits metal from wire feedstock layer by layer until the part reaches near net shape and is ready for finished machining.
So later you can do machining.
Deposition
So it
rates
has a
can
proper
range from
surface
7 to
finish.
20 pounds of metal per hour, which is significantly more efficient and cost effective than selective laser sintering processes that utilize messy powders. In addition, a dual wire feed system can be utilized with the EBAM process to increase deposition efficiency, as well as to easily switch to different deposition materials. So whether you need to produce a functional prototype or a run of production parts, the possibilities are virtually endless. Our technology partners include the Department of Defense.
So this is how the EBM process works. So you'll be having a wire form raw material. So based on the material required, and you will be having a electron beam solidifying source. It will be solidifying on the rotary table. So in that way, your complete model will be built. So that is about EBM process. EBM process. So next we have material jetting. So which is similar to SLA process, like you will SLM process. So you'll be having a powdered raw material. So here you can see which will be in the 60 to 32 microns. So liquid resin is heated at 30 to 60 degrees to adhesive the. So what happens here is like you will be having a powder raw material. It will be deposited, and on top of that your material will be deposited, which is in between 30 to 60 degrees centigrade, and it will be subjected to UV light source, which cures the resin. So in that way your complete model will be printing in layer by layer format. Like after jetting the material, your build plate will be lowering by the layer resolution which you define, and after that your next layer will be recoated and material will be jetted so that it will solidify the part. So that process continues. Here you can see. So here we have material container. So from where the material is coming, and you will be having UV curing light here, and you will be having the inkjets similar to our normal printers, and you will be having a part support material, build platform, and elevator. So this is the build platform we have. So that's how this is the construction of material jetting uh, technology 3D printers. So you can see the video next. So the material is being jetted from the ink heads, and your UV light will be solidifying the part. So after that you can remove the part. So whichever is the clean part or the actual part is there, you can use. Other support material part you can throw it. So this is a curing chamber. So if the material is partially cured, you will be keeping in a curing chamber where you will be having what is UV light in all 360 degrees, and it will solidify that. So in that way your material jetting will be working. So here you can see, so the one which are in black color are the actual part, the white color part is support part. So in that way your printhead will deploy both the materials, like it will deploy the support part, it will deploy the model part. After deploying your what you can say UV light will solidify that. After completing one layer it will go down and the next layer will be jetted. So in that way the process continues until the complete object is built. So that is about the material jetting. So this is binder jetting. So where it will be jetting the binder instead of material. So the material will be deposited by the recoder, and this binder will be jetted from the jetting head. So it is similar to SLM process. So but the solidification source here is a binder. So which will be jetting from the extrusion head. So here you can see, here you can print sand parts also. That is the advantage of binder jetting. You can see in the video.
Binder jetting additive manufacturing is a process inspired by the technology of inkjet printers. In this process, a liquid binder is selectively deposited on a powder bed with a printhead. It is a growing process that allows the production of parts for the manufacturing, medical, and dental industries. This technique enables the production of metallic and ceramic parts as well as sand molds for castings. To start the process, a 3D drawing is imported into the printer software.
So which is similar to other technologies.
The
like
powder to be
3D
used
model.
is placed in a dispenser, which ensures a constant supply during printing. First,
Your
a
record is
powder
ready.
layer of a specific thickness is spread. Thereafter, the printing head, moving on 2 axes, projects the binder where necessary. Before moving on to the next layer, the solvent contained in the binder is evaporated by an incandescent lamp. The powder bed is then lowered and a new powder layer is deposited. Therefore, the production takes place in a series of steps that build the part layer by layer. When the cycle is completed, the binder is cured by placing the container in a furnace. The temperature and time depend on
There's
the
a
type
curing
of
chamber
binder
we have.
employed during printing. After this step, unbound particles are removed to reveal the part or the mold. After this step, the sand molds are ready to be used in foundries. The metal and ceramic parts must undergo sintering, infiltration, heat treatment, or hot isostatic pressing before being used.
So that's how the binder jetting works. So which is similar to the material jetting, but here you will be jetting the binder instead of material required. And you like first you will be depositing the powder raw material, then your binder will be jetting and it will be solidified using high intensity or high temperature uh, light source. So after doing that, you'll be keeping it in a curing chamber. So where it will be providing the high intensity light in all the directions such that the uncured binder or unevaporated binder will be jetted off, and in that way your complete process works. So if you are going to print any metal powders, then you have to place that in a heap process or in a sintering process such that your what is the partially melted material like metal parts can be remelt and they can solidify. So that's about the binder jetting. So coming to pioneers. So here you can see there are 3 pioneers in binder jetting. One is X1 metal, one is voxel jet, one is HP. So here the major difference is like in voxel jet you can use sand also as a raw material. So here we can use it mostly for metal powders, and here the quality is also more when you're since voxel jet is used for sand, and these are the build areas we have. So this is about the what you can say binder jetting. So these are the different classifications we have when you are going for additive manufacturing technology. If you are having any doubts, you can please ask. Meanwhile, as I said, so we are conducting this what is it, webinar as a part of a promotional activity of a Future Skills Prime program. So as I said, Future Skills Prime program is a initiative to develop what you can say to update the manpower in emerging technologies. So in that we have 10 different technologies. Sorry. So among that, additive manufacturing is one. We have the other technology like data to software. We have like blockchain technology. We have rapid prototyping and the other technologies also. So if anyone has interest, like I'll be showing you. You you can register. Like you can go to FutureSkills Prime portal. So we have a portal for this where you can register yourself. So hope you are able to see my screen. So this is the Future Skill Prime program portal. So where we have different courses. Among that, additive manufacturing is one. So if you want to choose any course, you can go for here courses section, and you can choose the course from here. So here we have different courses like artificial intelligence, big data analysis, blockchain, cloud computing, and cyber security, and IoT, Internet of Things. So and here we have 3D printing. So if you are interested in learning further, like 3D printing, like here we just classified the IT manufacturing technology. We have a lot of things in this also. Either you can go for bridge course. We have 4 different courses, but here currently bridge course is what is enabled in the platform. So which is a 90 hours course. It is a self-paced course also. Like you can learn it whenever you are free. So here you can go for 3D printing and you can select the course. So so this is a course which we have, like we are offering for 3,400, and top of that, government is providing the incentive of 50% after completing the course. Like once you get certified, you can produce your certificate and you can get the refund of the amount up to 50%, like 50%, not up to 50% off, or it will be reimbursed to you once you get certified. So this is about the course. So you can learn more, like what is the duration of the course, what all topic. Like we have 3 modules inside. One is related to design, one is related to 3D printing. Like we'll be showing different technologies in detail. We'll be showing the process. We have machine, like you have, if you are okay to come to what you can say your resource center which is nearby, you can go to that resource center. You can have practical, like hands-on also. And we have design for additive manufacturing. So we have 3 modules inside this. You can learn that by registering here. So the with GST the course will be around 4,000 and you will be getting maximum of 50 percent. So you can get the course. So this is about the bridge course we have, which we are offering on 3D printing. Uh, if you are having any doubts, you can please ask. No, sir, like a participation certificate, as it is webinar, we won't have, like we are going to conduct GOT program in nearby in December once again. So if you participate that, like it is a 1 week program, which is 40 hours program. So you can participate in that program and you can get certified with government officer training certificate. So this is just a promotional activity which we are doing, like a 1 hour webinar. So we have like a 40 hour course, like without any fee for government employees. So we'll be sharing that to you, like once we are confirmed with the dates of the training. Yeah, it is completely online training, sir. Like 40 hours completely online training. Morning it will be 2 hours, after 3 hours. But 3 hours we will be having 1.5 hour practical session. We'll be giving different software. Like I just said, we have slicing. So in slicing, we'll be explaining the slicing software, and we'll be like giving hands-on also. So yeah. So if anyone is interested in registering with this course, you can please register for the bridge course, which is very helpful, as additive manufacturing is one of the emerging technologies, and it is also a part of what you can say Industry 4.0, which is digital manufacturing. So if anyone has doubts regarding today's topic, you can please ask, or you can write us to 3dprinting@cdac.com also, or else we can wind up the session as we have already exceeded time. So. Yeah, thank you everyone for the participation. So if there are no doubts, we can wind up. If you have any doubts also, you can mail us later. Like if you want to undergo any kind of training regarding IT manufacturing, if you need any help regarding 3D printing, you can also write us 3D printing at @cdac.in. Okay, thank you everyone for the participation. We can wind off now. Thank you.